Okay. Thanks, everyone. Sorry for the slight delay there. Welcome to one of our first hybrid seminars at UCI ESS. So today, Dr. Colin Raymond will be speaking to us. He's visiting from NASA's Jet Propulsion Lab, where he is currently a postdoctoral research fellow. Prior to working at JPL, he graduated from Cornell with a BS in atmospheric science, magna cum laude with distinction in research. And in 2019, he completed his PhD at Columbia in ocean and climate physics. He's, in my opinion, at the forefront of work on humid heat extremes and how they're changing with global warming, which I think we'll learn a lot more about today in the seminar. And it's really great to be able to hear it straight from the horse's mouth, so to speak. He also plays a key role, and this is how I've interacted with him before to some degree, in organizing the research community around compound extreme events, leading workshops and conference sessions and synthesis articles that really helped coalesce the community around this important topic. So today, the topic he's presenting on is called Sharpening the View of Extreme Heat Stress, Global and Regional Patterns and Their Drivers. And yeah, take it away. Thank you, Colin.
Thanks, Jane. Yeah, so as the title suggests and Jane's introduction kind of paves the way toward, this talk will be sort of a skip and hop over some of the work that I've done in the last couple years, I guess basically since 2020, around extreme heat stress and various kind of aspects of its impacts. And in thinking about the impacts of extreme heat stress, one naturally has to question kind of the processes that lead to them. And those processes, both when we started kind of thinking about what they might be, and also as we've continued the work and developed our understanding, have proven to be just as diverse as we first anticipated. So I chose 4 photos that actually are not just random mixes of images, but actually represent 4 of the key global hotspots of extreme heat stress. And one may notice maybe the one thread that connects all of them is that there's quite a bit of water pictured. In 3 of them, it's on the surface in rivers or oceans or lakes. And then in the bottom right there, that's the eye of a tropical cyclone. So there's a lot of moisture already in the atmosphere. But of course, to create extreme heat stress, obviously that moisture in the top left and the top right and the bottom left has to get into the atmosphere, and it has to stay there at the level that we all experience extreme heat stress, which none of us are taller than about 2 meters. So it's basically the bottom 2 meters of the atmosphere and what we're most interested in. And that can be a challenge because anything above that, which we consider weather, is relevant in many respects to, for example, precipitation, but not so relevant necessarily to heat stress if it's kind of distinct, what's happening at the lowermost levels of the boundary layer versus the rest of the atmosphere. All right, so with that, just try to adjust the microphone to be accurate. And I've done this work with a bunch of collaborators. I think I may have left a few out as I've added more work to this presentation. I said that over here. All right, so I'll start off briefly with what we know about extreme heat in general, and I'll try to move a little bit quickly through this, more background stuff, but not too quickly to lose anybody, hopefully. So we know in general extreme heat is very certain to increase and has very high impacts. There's right now a lot of stories about extreme heat going on in South Asia, pre-monsoon, something that's happened since time immemorial, but of course is getting more severe with climate change. And then when you consider humidity, in addition to high temperatures, there's a relevance that's particularly strong with respect to human health. So, for example, admissions to hospitals, deaths from heat stroke, for example, and then also around energy demand. So that's connected to health, but more directly, say, the electricity needed to run air conditioning and that can lead to, for example, blackouts like we've had, or brownouts like we've had in California in the last couple of years during some of the peaks of the heat waves. And I've used myself and many other people have used various different metrics for humid heat, but for the purposes of this talk, I will try to keep it very simple. So just think of humid heat as an oppressive combination of temperature and moisture in different combinations that leads in some vague hand wavy way to heat stress. And I purposely took out all the units in these slides so that they're not distracting. And of course, you can look at the underlying papers if you want to know, some of the values. I left in things like temperature, but don't worry about the units of moist static energy or what they mean. All right, so then I'll have a couple of slides here talking about, illustrating some of what we already know and to kind of ground the remainder of the talk. So if you look at the trend in a high level of humid heat, so this is the level that's about the same as the annual maximum heat stress value in Washington, DC. So pretty unpleasant. That has more than, I took off all the numbers, but it's more than doubled in 40 years. And there's pretty good agreement between stations and reanalysis about that. And then the same paper from 2 years ago showed that the very hottest places are just about at that level where it's not possible to survive indefinitely without artificial cooling. And that paper then inspired some of the further, I won't talk about that paper too much, but I'll talk about a paper, several papers that were inspired by it to sort of understand what's going on there. But I will say that what we don't understand that well is what the impacts of those things are, because they're happening in places where there's not good impacts data. So it's very hard to know how much people are suffering, or perhaps why they're not suffering. Obviously, socioeconomic inequities are probably playing a role in that. For example, migrant workers in the Persian Gulf are not well documented in general, and certainly their deaths, potential deaths from heat stress, are not well documented. But these things are happening briefly, and so they're hard to measure, even in a place like the United States. Another broader point about heat stress is if you just survey the whole world and look at latent heat and sensible heat and how they combine to form heat stress. In the more extreme places, so for example in South Asia, there's a very large contribution of latent heat to the total. So that's the moisture in the air relative to what you would measure on a thermometer. And then, similarly in the tropics, it's relatively large. And of course, by the time you get down to the poles or the drier mid-latitudes, there's very little moisture, so it doesn't sort of matter as much. And this suggests that as the planet warms, there'll be a larger contribution of latent heat to the total, so it matters more to consider the humid heat relative to just heat. Then I won't dwell on this one too much, but there's quite a few studies now showing the contribution of the land surface to the total to humid heat events. And that can happen both because there's a flow of air that's being moistened by, for example, vegetation, and that can be amplified further by irrigation in those areas. So the bottom study found that the irrigation in northern India and northern Pakistan is increasing, or has been increasing in the last few decades, wet bulb temperatures in those areas by about 5 degrees Celsius, which is a huge amount. It's about the difference in wet bulb temperature between here in the summer and the East Coast, Washington, DC, for example. So anyone who's walked around the National Mall in the summer knows that that's pretty tough, whereas Orange County is significantly more comfortable, and that's kind of the difference that's been happening just due to irrigation in these areas, which of course have many socioeconomic vulnerabilities as well. And then the last slide of this genre here is that humid heat has pretty significant seasonal and regional peaks that one may or may not expect a priori. So these are two figures that I've made. One from a paper came out 2 years ago, showing that the peak occurrence of humid heat in northwestern South Asia occurs right around the time of the monsoon onset. So suggesting that there's a sort of sweet spot there between there being enough moisture to drive humid heat, but not so much that it is leading to precipitation. And that is something that needs to be investigated further. We did a pretty rough approximation of it here, but it seems like a compelling potential process-based kind of analogy. And then a more recent thing that I haven't published yet, but is still in preparation, is I guess even more general, just looking across the central US. If you just do a basic correlation between temperature and moisture in terms of daily maxima in the summer, there are, in a relatively small region, this, it's 1,000 kilometers or something across, the correlations range from about positive 0.6 to negative 0.6. And you can see, for example, over the lakes, the correlation is much higher than over the land. You can see the Corn Belt in Iowa is significantly more correlated between temperature and moisture than other areas that are not so heavily cropped. So those kinds of spatial correlations are, I think, not that well appreciated in terms of the potential to drive joint extremes, which of course is what humid heat is all about, right? It's a joint extreme of temperature and moisture. And then you can see sort of in the bottom right there, places where temperature and moisture kind of vary in a more stochastic way, the correlation is close to zero. But further north, for example, the temperature and moisture kind of come in the same episode. So there's a meteorological sort of way to understand this, which I've been trying to do, but I think there's much more to be done. So this is the kind of plot I make to make that argument anyway. All right, so now on to the big remaining question. So the core of my talk, I guess, will be walking through this study from last year, where taking all the information that I just presented, essentially, we felt like there was still a lot to understand, and that can sort of be summed up by looking at this map that was figure 1 of the paper, but was sort of what we were looking at to base the study on. So we focused on the regions in black, in the black boxes, but looking at those and also across the world generally. And again, I took out the units, so just purple and red are the highest values of humid heat, and the all-time maximum from Euro 5, the analysis. You see very specific hotspots, right? So there's kind of a general zonal pattern that some of these tend to be in the subtropics, for example, but it's very, very concentrated. And it's not necessarily what you might expect from a map of temperature, right? So for example, the Sahara is not that high. I mean, it's lower than central US, for example. You also see quite a few coastal effects. For example, in that box in Eastern India, and also in places like Northern Australia. If you kind of squint, you can see northwestern Mexico is has very, very high humid heat. And then, of course, why, trying to understand, in a way this can be understood, the question can be turned around, why is there not very extreme humid heat in a place like West Africa compared to, say, South Asia or Southeast Asia even? So that's what we were kind of basing our questioning at, trying to understand this. So I guess I'll kind of jump to the conceptual framework that we sort of developed and roughly tested with the observations. So our conceptual framework is essentially this, and this is, up for debate, but this is what I would propose. So the first point is that relatively local or regional meteorological processes, or one might say climatological processes, the set of things that happen in a given place. For example, here in Orange County, that would include, the sea breeze, the Santa Ana winds that happen occasionally, stuff like that. Kind of set the distribution of possibilities of humid heat values over the course of a summer. One place might be relatively constrained, like place 1, another place might be more variable, like place 2. And then relatively relatively speaking, mean temperatures or mean SSTs in the tropics, those are somewhat interchangeable, determine roughly, again, the interannual and long-term warming variations. So that distribution is essentially shifting somewhat rigidly from year to year. All right, and then to back up the bottom part, sorry, the mic keeps sliding. To back up the bottom part, we made these figures showing that first, if you look historically, the interannual correlations between the extreme humid heat occurrences on the y-axis and the tropical median humid heat, or even SSTs, are quite good. So the tropical median SST variations explain half of the total variation in humid heat. And you can see, of course, El Nino ENSO is playing a significant role there, as well as long-term warming. And then also, if you look across models, for example, CMIP6 models, 90% of the variation in humid heat change across those is explained just by the change in tropical median SSTs. So we haven't actually published that or explored it further, but you can see, the models line up well, plus they kind of extrapolate out the observed trend. So that's the origin of the basis for asserting the second point. And then the first point is what I'll kind of dwell on in the remainder of this discussion. Except first, I guess I'll emphasize that the interaction of those two kind of frameworks means that if you want to understand what's controlling the highest humid heat values in the hotspot areas, or even where the hotspot areas are, you have to think about the fact that basically you need heat and moisture. Again, this is kind of hand wavy, but I think it's about as good as we can do. You need considerable heat and moisture in or near a location, so it can be kind of advected to that location, or it can be generated locally. And then, and that kind of drives, say, the 90th percentile or whatever, the typical kind of summer, extreme event. But then to really get the all-time maximum event, you need the possibility of some kind of amplifying process to drive exceptional accumulations of heat and moisture in the boundary layer, and keep them there long enough that they're not going to say just kick off a thunderstorm, but will actually they will amplify upon themselves and lead to heat stress that we measure. All right, I actually skipped that, I think. So as a first point of justification, if you plot the sensible heat, so basically just the temperature on the left and the maximum SSTs on the right, you can see they kind of roughly line up with the humid heat map. And if you're not convinced by that, I guess I will show some of the hotspot results and demonstrate some of the processes that led us to this conclusion. So I'll show results for 3 of the hotspot locations. One of them is the Persian Gulf, which really takes the cake in terms of the most extreme humid heat anywhere. And again, this is from that paper. So on the left, I've already gone and circled 2 of the important parts. But what that's showing is it's a composite of humid heat, again, red higher, orange and red higher, blue lower, for a bunch of different extreme events. And the arrows are showing the vertical motion, and this is composited over the southern Persian Gulf. And what you see is that there's a lot of humid heat, and it's right near the surface. So you can see on the left, maybe it's a little hard to see, the top of the hill, which is shown in the gray. So this is a northwest to southeast composite. So you're basically looking from Iraq, say Baghdad, down across the Persian Gulf, and then the hills are in like near Oman, and then it goes out southeast of there, back over the ocean. So that area with the orange and yellow is directly over the Persian Gulf, and the winds are from the northwest in the summer throughout the whole area. So as soon as the wind gets over the water is extremely hot, and starts entraining evaporating a huge amount of moisture into it and drives the humid heat value is very, very high. But a lot of that heat and moisture is concentrated just in the bottom 100 meters or so of the atmosphere. So a big question is what exactly is causing that to be trapped, quite so tightly. I had some interesting conversations already this afternoon about the possibilities there, and I guess I don't fully understand myself. I mean, you can see that there is downward motion stability in the mid and upper troposphere, and I should point out the scale is nonlinear. So the bottom part of the boundary layer is actually occupying a large portion of the vertical profile here. But as to what's keeping it in the bottom 100 meters as opposed to the bottom 1,000 or 2,000 meters, I confess to not being completely sure. And then if you look, at this as anomalies in terms of the overall, you can see that there's an anomaly kind of in the same area that there's the extreme. And sorry, the cross section there is kind of zoomed in on the right side of that plot. So the Persian Gulf actually, despite its extremeness, is quite simple to understand in a way. It's just the SSTs are extremely high, 34, 35 degrees. That evaporate as the water crosses it. As the air crosses it, the water evaporates a huge amount, and then it sort of just hits the shore, the southern shore, and causes extreme heat stress in a pretty tight area before it sort of dissipates into the desert. If you look at a place like Pakistan, you get a rather different story, and this aligns with some of the studies previously about Pakistan. What you have here is you have air that is ascending the Indus Valley, so the flow is from the southwest, if you look at the map. And then as it ascends the Indus Valley, it both warms and moistens. So there's both sensible and latent heat fluxes that are going into it. And there's some kind of mysterious right now role of the topography. You can kind of see in the rightmost plot with the cross section, the anomalies are sort of concentrated right along the slope, and we have a few lines of evidence. We don't think that's just a reanalysis topographic effect, but I suppose it could be. And again, you have sort of a layer of stable air kind of trapping things up above. And if you look at Eastern India, so Eastern India versus Pakistan is quite an interesting contrast, because Eastern India is much more humid. So you have much more humidity and tendency to precipitate in general. And so the extremes are kind of not as extreme, and they're more driven by sensible heat fluxes, and I'll kind of illustrate that in a second. Okay, so yeah, actually, so if you focus on the bottom, so we did a budget for Pakistan and Eastern India, and what you find, if you focus on the colored bars, is in Pakistan, the anomalies are largely related to latent and long wave fluxes. And the net looks relatively small, but it's not that small really. And then in Eastern India, it's largely a short wave picture. There's a latent heat flux contribution as well. But the fact that the skies are clear makes a big difference, because typically at this time of year, June, July, it's pretty humid and cloudy in Eastern India, whereas Pakistan is dry and sunny, and so in Pakistan the humidity makes a bigger difference basically than it does in Eastern India, where you sort of need a higher temperature to drive the extremes. So the extremes are kind of all about what happens typically, right? It's kind of a truism, but also very important because it implies a sort of regional perspective in looking at extremes in this joint parameter space. And maybe I'll kind of move through this one a little quicker, but one thing we found very interesting, and I hope, well, I don't hope, but if someone else could verify this, it would be fascinating. But as far as we can tell, this is the case. So in the southern Persian Gulf, not only is there extreme humid heat, the most extreme actually anywhere on the planet, but it tends to happen in late evening, not during the afternoon. And you can see that the diurnal cycles, this is showing the diurnal cycle during the peak of heat waves composited. And there's both a land and an ocean. The land and ocean are next to each other in this. In these plots, it's something like 100 square kilometers in each, you know, of the grid cells being put together. So the diurnal cycle over land is much higher, and the humid heat peaks around midnight local time. And so now in each of these subsequent figures, I've put a different variable on the top and then put the humid heat down below for reference. And the orange dot is supposed to show the time at which the peak humid heat occurs. So in temperature, right, if you focus on the top left, the temperature is pretty much what you'd expect, right? It peaks around early afternoon, kind of drops off. And then the red, I should say the red and the red is extreme humid heat events, and the blue is the rest of the warm season composited. So over land, it's about the same temperature, but it's more humid, especially at night. There's really not much difference during the day. And the moisture is significantly higher at night. And it's similar to the ocean. So there's a marine air, basically signature over the land that there isn't normally. The PBL height, the planetary boundary layer height, is again kind of very low. And the wind direction sort of gives it away. This is a little hard to understand, I guess, without looking at a map, but this is the southern end of the Persian Gulf. So a northerly wind is a sea breeze. So essentially, normally, the wind is much more westerly or southwesterly. And during these events, you have a much stronger northerly component. So the red line is close to the top or close to the bottom. I suppose that must be a better way to represent this, but this is about the best we could think of doing. So essentially, you have a much more consistent sea breeze during these events, and that is driving these nighttime humid heat peaks. All right, and so now we'll go back to the whole kind of global picture. Just pause for a second to let that all sink in. So we decided that an interesting thing to do, and we'd try something and let other people maybe try to refine it, would be to try to predict with kind of one eye covered up, covering one eye, and do a pseudo prediction of where the global humid heat hotspots are. And we sort of played around with this, and it's a little bit artificial, right? Because we sort of know the answer and we're trying to predict it. But we thought it would be an interesting exercise because, because of the initial question, right? We don't know what is causing certain places really to have extreme humid heat, and not others, West Africa versus South Asia. So if we thought if we could identify some of the key factors that would be useful kind of both in our meteorological, seasonal kind of way, but also in a long-term climate change way. So we decided kind of both based on theory and our analysis of the observations to pick out a few variables. So we picked 6 things in the end, representing either high SSTs or high latent heat fluxes, vertical stability, and then we sort of cheated a little bit by picking like low elevation, excluding deserts and rainforests, just because we know humid heat doesn't occur in those places. And empirically moderate places of more moderate relative humidity kind of have this right balance of temperature and moisture that can lead to joint extremes. And then places with high, either mean, there's kind of a mix of means and extremes that can talk about the details if anyone is interested. Shortwave and longwave radiation. So we tried very hard to kind of exclude, at least in an explicit way, any direct sort of temperature or moisture of the atmosphere. So all these things that sort of are contributing to, or might be contributing to temperature and moisture extremes in the boundary layer without directly measuring them. And if you put those things together, just measuring, so this is so orange here is showing which places sort of meet each one of these criteria. And then if you just add them all up, the dark red areas are the places you'd expect from those 6 factors alone to have extreme humid heat. And again, the green boxes are just the regions we studied in this paper. And if you compare that to the observed maps, that's the same data that I already showed, just with a different color bar. You can see, there's not a perfect match, right? But it is not too far off in a way. Depends how you consider this. But for instance, it does show the Persian Gulf, right? It shows Pakistan, parts of India. It shows Northern Australia, not too badly. Northwestern Mexico, kind of somewhat there. So considering that, I guess this is the first attempt that had been made, and generally people kind of hand wave about the subtropics versus the tropics, we thought this kind of more longitudinal identification of hotspots, at least to sort of 0 Earth order, was a reasonably good attempt. And I suppose it could be done better, right? But yeah, we were proud of it, I guess, despite its imperfections. All right, so just pause on that for a second, and then what I'll move on to next is a few different things that we've done, or that I guess I've led around humid heat and its relationship to specific meteorological processes. And I'll mostly focus on storms. So I have 2 kind of key things there. So the first point is that I've been doing a few things around the Midwest US, looking at humid heat. And to start off with kind of demonstrating the fact that there is a relationship. This is a composite for, as it says, top 1% humid heat events in the Midwest. And you can see that there's a very clear kind of story here where essentially you have wet soil, so anomalous precipitation around a week before, maybe 5 days before an extreme event. And then you have, after the precipitation, you have a big high pressure system, which in the Midwest means southerly flow from the Gulf of Mexico, essentially. So that's both bringing in moisture from the Gulf, plus there's sort of enhanced latent heat flux, again, kind of partially related to the Corn Belt, partially just, because there's lots of plants in the east. And that then drives a peak in the humid heat. And then sort of throughout that period, right around the peak, you have high shortwave, it's not shown, but you have high shortwave radiation, suppressed convection. I guess partly we've demonstrated that, and partly we sort of suppose that. So that is further work as well, but then you can see things trail off back to 0. Again, the time scale for these things is 5 or 7 days in the sort of in the mid latitudes. And then a similar kind of thing, I've been looking at atmospheric rivers specifically because they lead to sort of large scale correlated precipitation and moisture advection. And if you look again at the warm season, humid heat, within 3 days of an atmospheric river, within 3 days of an atmospheric river, the risk of top 1% humid heat is about double or more than double in some places and quite low in other places. So you can see there's some resemblance, right, to the map that I showed at the beginning about the correlation between temperature and moisture generally. So this is kind of a more specific, I guess, potentially operational meteorological insight into the kind of, if there's an atmospheric river coming, there's probably going to be humid heat, at least if you're in Montana, right, and to a large degree in the upper Midwest and the Northeast even as well. And then you can see also kind of closer to here, there's also significant relationships down in the sort of Baja California area, presumably related to kind of filaments of moisture that are classified as atmospheric rivers, but really are part of the monsoon. So the relationship between humid heat and the monsoons are quite interesting generally, and that is a big part of the South Asia story as well. And then I was just part of a paper that came out in February, I think, that did the same sort of analysis around humid heat and precipitation, but it's global. Simone Spicer led this and did a great job. And so what the color bar is showing on this big figure, the big map, is that so we defined something we called concentration. So basically, if there's a humid heat day, what is the chance, or how many other days, how many other humid heat days would you expect within a week of it on either side? So in that 14-day period around it. And you can see the peak value there is 8 or more, right? So that means that if there's a humid heat day in some places, that means half of the other days in a 2-week period are also humid heat days. And given the rarity of those days, this is a quite remarkable clustering in a temporal sense. And then you also notice that where those hotspots of clustering are, or concentration are not random, they're concentrated in deserts. And so we, to kind of justify this, picked out a few of the actual precipitation time series, showing the humid heat in blue and the precipitation in green. And basically the story, the story basically is, in places where it's dry, a little bit of precipitation goes a long way toward enhancing the moisture flux and driving humid heat. And I guess what's remarkable about that is these are deserts, so you might, in a sense, expect that moisture doesn't matter very much. But actually it does matter quite a lot, because moisture is it's consistently hot in, say, Iran, near that one, the rightmost red star. It's consistently hot in Iran and Pakistan, but what you don't have is the moisture. So when you do get the moisture, it's both hot and moist, hot and humid, hence the extreme humid heat. So one way of thinking about these joint exceedances, at least for humid heat, is sort of whatever you don't have much of, it's like an economic scarcity kind of argument. Whatever you don't have much of is what's most valuable. All right, and then I'm getting toward the end here. So the last section that I'll talk about is, again, work that's in preparation, but I think quite interesting in this context of regional humid heat exceedances. So I sort of happened upon the discovery that there seems to be quite a close connection between humid heat and tropical cyclones. And of course, Jane, I'm sure, has a lot to think about and has done great work on tropical cyclones and humid heat and so on. But so I guess first I'll explain what this map is. And this is a pretty severe requirement. So it's the all-time maximum humid heat value at a grid cell. This is from Aero 5, occurring within 24 hours and 500 kilometers of the center of a hurricane. So not just a tropical cyclone, but a hurricane strength tropical cyclone. And then the colors are just showing the year in which that happened. And you can see a pretty large portion of the global oceans are covered actually by this. And I suppose a few coastal areas probably as well, but it's largely a marine thing. Nonetheless, it seemed interesting enough to kind of explore a little more. And I'll show this map again because we actually realized that when you look at this map, you can see some of those tracks on this map. If you look at, say, the Western Atlantic or the Western Pacific. And not only that, but it's also, this is even harder because it's from a different paper and poor resolution, but you can even see it on this map. So I'll try with the cursor. You can see right there and right here. And again, the Western Atlantic right there. So it's not just an artifact of our, coding, a coding error or something. And then to explore that just a little more. So if you zoom in on the Atlantic, doing the same thing. So you can see, again, the colors. This was all related to Hurricane Bill in 2009 that made it all the way up into Nova Scotia and Newfoundland. And then furthermore, if you look at particular hurricanes, so for example, there's 4 hurricanes this happened with in 2010, and now the color on those is the day of the year. You can see it follows the track, the humid heat, for example, for Igor follows the track of the center of the storm, and it occurred on consecutive days, right? So it was happening sort of in association with the storm as it moved along. So I thought that was pretty pretty neat. And then the last thing that I did around this was I then went and for all these different events, I composited both. So centered around the storm, I composited the humid heat, the extreme humid heat occurrences, and then the temperature, specific humidity, and vertical velocity. And I think there's a lot more that could be done here, for example, at different levels. This is just kind of a justification, exploratory thing. But the main points, I guess, that are interesting about it are that and I only took Northern Hemisphere to make things simple. So the extreme humid heat values are concentrated in the northwest quadrant of the storm. And you can see that the temperatures are somewhat higher in the northwest quadrant than maybe in the other quadrants. Specific humidity, maybe a little bit. And the vertical velocity, is maybe a little bit more negative. So basically, it's a little bit hard to tell maybe just at the 1,000 millibar level. It's kind of a lazy analysis, but the argument is maybe what's happening is temperature and moisture are a little bit higher in the northwest quadrant, and the air just happens to be a little more trapped. And I guess someone who knows more about tropical cyclones could say more about the mechanisms here. But I guess in any case, it's certainly pretty clear that the northwest quadrant is a sweet spot for some reason. And I guess in the context of kind of compound heat and tropical cyclone, landfall effects, important to think more about. And then I guess the last figure basically that I'll show, and this is something that I actually put together for sort of a risk-related presentation, but I guess it's kind of connected in the sense that it's not just storms that drive humid heat, but other things as well. As the top left suggests, this is related to drought. So if you take a scatter plot of just daily humidity values in the Amazon, don't worry about the units there, I should have removed them, against the standardized precipitation evaporation index from very dry to very wet over the first 27 years from era 5, you can see there's not a whole lot of correlation going on. There's maybe some suggestion that when it's very wet, humidity tends to be lower, but that's kind of about it. But then when you include 2018, actually this huge tail appears where very high humid heat values occurred at relatively low or dry SPEI values. So the sort of point about this is that there is this tail relationship that one might not have anticipated. And so I think there's some interesting questions, and I haven't looked at this more, but there's some interesting questions here about, first of all, humid heat, in sort of tropical and moist environments, and second, the potential usefulness of models to better anticipate extreme humid heat in places where it hasn't actually been observed, right? Because up to 2015, and this is across the Western Amazon, there had never been anything above, again, don't worry about the units, but 390, right? And then suddenly it's 400, over 400 as a result of this drought. All right, so the process-related summary, attempting to draw together the argument about why certain places have much higher humidity than others. Basically, it all comes down to two things. You need a good source of moisture, either from evaporation or evapotranspiration. And then you need something that sort of traps it below the planetary boundary layer, at least for some meaningful length of time, six hours maybe. And there's some contributions from shortwave and longwave radiation that help drive this, this concentration. And the key thing is you want a profile with a lot of moisture represented by dew point. You want a vertical profile with a lot of moisture near the surface. That's kind of the number one thing. And then I have a couple of slides here just about the impacts of extreme events sort of in general with respect to extreme heat in particular. So this is a different paper from 2020 that I led, thinking about how extreme events actually lead to impacts and sort of how they feed back, going all the way back to policy, culture, technology, and then everyone talking basically about the hazard of the event, causes impacts, causes response, and those all feedback. And then, with respect to heat stress, I would argue this is kind of how things look. So there's both physiological and sort of socioeconomic exposure and vulnerability factors. Combine that with the heat and humidity that I've been talking about, so that is what causes heat stress. That leads to various losses. There's a lot of literature about, you can actually measure like the effect on test scores of heat stress. Of course, health impacts, financial losses if people, work outdoors or something and can't work because of the severity of the conditions. And then, whether that leads to changes in policies of equity, either has a positive or negative feedback on many of these things, including, for example, if we plant more trees or something in a city, then that, might lead back to here and affect the heat stress. Or maybe we irrigate a lot and that actually increases the heat stress. So there's a huge amount of things there. And then I guess the last thing that I'll add, and this is, I guess, a little bit of a plug for a recent paper I was a co-author on. I would actually say that representing humidity accurately is not just a question of understanding the Earth. I mean, it is, but it's also kind of a question of equity. So if you don't include humidity, because humidity is largely concentrated in the tropics and subtropics, which of course is where a lot of the vulnerabilities are, you get a very different picture of kind of what global warming, the signature of global warming looks like. As you might kind of anticipate already from looking at these figures, if you look at, this is just regular temperature, a place in the Arctic and a place, say, in northern India, or Pakistan actually, there's not much happening really in Pakistan actually in the last 60, 70 years, but if you include humidity, this is equivalent temperature. If you include humidity, actually the change is pretty similar in those places. So just looking at temperature works in some sense, but not very, it really undersells the changes in some of these most vulnerable places. So I'll just leave up the conclusions and take any questions and interested in chatting at the coffee social hour as well. Thanks.
Great, so I think take questions from the room or from Zoom, I guess. I think people on Zoom, either raise your hand or put in the chat. Colin, maybe say, just say people on Zoom can either raise their hand or put a question in the chat. Yeah,
if you're on Zoom, you can either raise your hand or put a question in the chat.
Well, I have a question to start things off. I maybe predictably think the composites you made for tropical cyclones are cool. And I'm wondering, did you make those just for the northern hemisphere, or does that include the southern hemisphere too?
Well, just the northern hemisphere, because I was, the microphone keeps falling, sorry. Just the northern hemisphere, just to keep it simple, but
right.
Yeah, it could be done. It could be adjusted, I guess, pretty easily for the southern as well.
Because I mean, like to evaluate some mechanism related to, like, if you think about the circulation of the tropical cyclone, it's going the other way in the southern hemisphere. So I guess if it's like something to do with the circulation, if you did it for the southern hemisphere and saw, I guess it was in the southeast quadrant or something, that might be interesting.
Yeah.
See if it's a robust mechanism.
Yeah, you're right. That would be a sort of first pass way of figuring out if it's some kind of coincidence or if it really is the direction of the circulation that is
right.
Explaining that.
Yeah. Anyway, I think that's cool.
I'm happy for more ideas of how to make that better. Yeah, thinking about should I make something? Should I make some composite at 500 millibars? Or, I don't know, but I haven't finished that kind of work. So
yeah, no, it's really cool though. I mean, the other thing I was wondering is, like, if this is this just a phenomenon over the ocean, or is there evidence that there are human heat extremes coinciding with tropical cyclones close to, like, in coastal regions as well, which I'd be happy to talk about. But yeah, I have your thoughts on that.
Yeah, I'm not completely sure. I I think it's plausible that it might happen along a coastline, you know, particularly a small island that is very marine influenced. But yeah, I'm not absolutely sure. I guess there's also some possibility that the sort of brown ocean effect could be relevant there as well, and especially if one weakened the analysis a little bit. I mean, it's just looking at all-time maximum values, right? If you just look at the 99th percentile, there might be a much broader set of places, including land. Yeah, that are correlated.
Cool.
Jared, yeah.
I was just curious, you know, you noted that a lot of the interesting locations are subtropical and coastal. And I am curious if there's any relationship with the urbanization of the areas. It's a lot of cities tend to be built on coastlines, and a lot of people live in the subtropics.
Yeah, that's a great question. And I would say to first order, I don't think so. But yeah, I mean, I guess my work does kind of beg the question in many ways about what is the effect of urbanization in all of this. I mean, given the breadth of the trends, I don't think it's affecting the trends, you know, in general, but in a specific place, it's certainly, you know, I didn't adjust for urbanization or anything. So yeah, I've thought a lot about what it means for there to be, you know, for Dubai to have gone from a small, you know, town to a mega city in 30 years. But I was actually just chatting with a professor from a university in Saudi Arabia, and they have a bunch of money now to look at that kind of effect in the Middle East. But according to him, no one really knows what the effects are to sort of any appreciable degree. So yeah, if you want to look at that, I think it's a very open question. Yeah. It's a question from Jim.
Yeah. So the question is, oh, Jim, do you want to just say the question? I'll just read it. How does humid heat versus dry heat affect air quality? Does the change in air quality amplify mortality?
Yeah, thinking about the best way to answer that. So I guess first of all, I don't know per se. I guess I just know proxies of air quality, which are basically stability of the boundary layer. And I know, I mean, a bunch of the humid heat sort of situations that I've been talking about are very dependent on having a stable boundary layer. Not all of them, but many of them. And I suspect the answer is sort of highly regional. And yeah, I guess I'm not sure, but that seems like a good question to pursue. Yeah. Sorry, I can't provide more detail on that.
Yeah, go ahead.
Hi, I like your talk, and I have a question about one of your correlation map. I think it's one of the few first slides.
Yeah, the one for the US.
Yeah, I was wondering like what decided the design of this correlation.
Okay. Yeah, I can kind of partly explain that, I guess. I guess for me, when I think about humid heat from the work that I've done, I kind of first think about, and I guess I alluded to this, but it's hard to explain, so I think I didn't explain it that well necessarily. I kind of think about what is the dominant warm season meteorology in a place, and then I think about sort of what are the anomalies in a sort of, you know, meteorological process kind of based sense to that general picture. And of course, this is the correlation, so this is kind of the general picture. But the rest of the talk was kind of talking about, you know, the anomalies. But you know, the point of this map was even the correlations are kind of variable, you know, in a climate sense, not even a weather sense. And you know, here those the processes that are relevant, you've got basically you've got these big high pressure systems that are that last 3 to 5 days that are basically, that are centered, so, typically around sort of the Illinois, Indiana kind of area. And of course, with the clockwise circulation, you have a southerly flow. So I think what's happening is you have a general correlation in this upper Midwest area because the southerly flow is both bringing warmer air, from the lower latitudes as well as moisture from the Gulf of Mexico. And then it's kind of maybe locally enhanced by the Corn Belt. At least that would be my hypothesis. I haven't proven that or anything. And then similarly over the Great Lakes, hotter temperatures, have a higher vapor pressure deficit, so there's more evaporation. And of course, being a lake is an infinite supply of water. So I guess it's kind of the fact that there exists these hot and dry weather systems in the summer over this region. Whereas in the high plains, for example, the conditions that lead to high temperatures are not the same necessarily as the ones that lead to high moisture. So basically the direction of the winds, you could say, are different when you have positive and negative temperature and moisture anomalies. Whereas in the upper Midwest, it's the same thing, right? It's the southerly flow. That's my kind of first order understanding of it. So there's an anti-correlation, a positive correlation, and not much correlation over here. And I put Western Edge Bermuda high because, basically it's just a mix of things going on, and there's not as much variability down here. And so without much variability, in general, it tends to lead to sort of a messy correlation, absence of correlation.
So, like, for your explanation for the positive correlation, it's like the southern wind could that also be applied to the high plain? Like, basically like that, if you have a northerly wind, it carries the moisture from the Pacific Ocean. I don't know. It's like, you could just say.
Yeah, it's certainly a bit complicated. I guess, I would say that the upper Midwest, the weather is sort of more organized. If you think about it, if you think about sort of a week or 2 week period here, you have hot and dry and then cool and wet, hot and dry, cool and wet. And in the high plains, it's not the same as that because basically you have wind more from the west and from the south. And those two components you have basically heat. You have hotter temperatures and the wind is from the west, and the moisture sort of comes from the south or southeast. So they sort of almost can't happen at the same time. Yeah, this is a little bit different, but there's been interesting work about correlations between wind and precipitation in the UK, and they found that on the west coast they positively correlated, on the east coast they negatively correlated, and it's kind of the same thing. On the west coast, you have a westerly wind, which is bringing both basically precipitation and kind of gusty winds. On the east coast, it's the other way around. Yeah, so I think this is kind of a broader principle. Yeah. It's a good question.
Any other questions? Otherwise, people can still chat with him at the coffee hour. Everyone, especially grad students. Yeah. All right. Maybe we'll wrap it up. Thank you so much.
Thanks, everybody.